This is the main plate for the pocket watch I'm currently building. It's an important part of the watch because it defines most of the bearing or jewel positions. In many cases, jewels are pressed directly into the main plate, but in my case most of the bearings are contained in separate parts called cocks, potensors or bridges. Yet the main plate is still responsible for accurately locating these components. And accuracy is vital here. These jewels can be held in any way you like, it doesn't really matter, but what does matter is their position. Before we have a closer look at the jewels, let me first show you how I fit this potence. The jewels themselves are made from a synthetic sapphire, which is a very hard material. That makes manufacturing them quite tricky, especially considering their size. I put this Swiss-made Seitz jewel into a scanning electron microscope to learn more. As we zoom in, you can start to pick out more details, such as lapping marks, and you can even see the odd bacterial cell if you look closely. Let me zoom in far beyond the magnification we can achieve with optical microscopy, and you can see all the marks left from the manufacturing processes, both in the hole and on the upper surface. I would like to bring your attention to these axial striations in the hole. Firstly, they are really small. I mean, the striations are only tens to hundreds of nanometers in size, so smaller than the wavelength of visible light, which means if you were to view this surface with the naked eye, it would look like a perfect polish. I believe these axial striations are caused by a diamond impregnated wire drawn through the jewel hole to bring it to its final size. But what I find particularly interesting are these circumferential striations, which look even finer than the axial marks. So perhaps these Seitz jewels undergo an additional finishing process where the bore is polished. Throughout the watch, I'm using a combination of these Seitz jewels and some cheaper alternatives, mainly due to the availability of different sizes. This is the bridge for the third wheel, which I'm currently fitting with one of the cheaper jewels. And I can hear you asking the question, what's the difference in quality between these two? Now, I can't speak for the material properties without further analysis, but the cheap jewel itself looks well made. The only difference I can see here is the lack of circumferential markings. If anyone knows why this is, or has any more information on jewel manufacture, please do let us know in the comments, we'd love to hear from you. To position the jewels in the watch, the main plate needs to be drilled with corresponding holes in the correct position. In the days before precision machines, watchmakers used these depthing tools to mark the positions of the wheels and pinions on the main plate by hand. Modern watchmakers, though, use a CNC machine or a jig borer to accurately position the holes in the main plate instead. For example, this is an SIP jig borer owned by watchmaker Jack Elam. Combined with the very accurate high-speed spindle and work-holding setup, Jack can position holes with a 3-micron accuracy. In the previous YouTube video, you may remember that I recently acquired a small precision milling machine, but at the time I originally made the main plate, I didn't have this, so my options for accurately placing these holes were quite limited. I don't have a jig borer, and as much as I love my milling machine, I think making a watch plate with this is probably asking a bit much. So my solution was to try a 3D printed master on the pantograph to position the holes. So I modelled a template, 3D printed it, aligned it on the pantograph, and went ahead and machined the watch plate. So the question now is, how accurate is the result? Jack kindly offered to measure the main plate for me using his optical measuring machine. We established what we thought would be a reasonable tolerance target, and the machine told us where we were in that range. Unfortunately, the result was actually pretty disappointing. We measured a mean error of -35 microns with a standard deviation of nearly 20 microns on hole separation. I was really surprised by this because corresponding parts fit nicely. So that implies that all the parts I make on the pantograph with this approach have the same error. With a bit more investigation, I realised the errors were not because of the pantograph, but because of the 3D printer. Now, I love 3D printing. I think it's an incredible technology, but clearly it does still have its limits. In this case, most of the error was caused by shrinkage of the 3D printed component, because obviously it's manufactured at an elevated temperature. I think it would be interesting to see 3D printers in the future compensate for this effect, but for now, if using this approach, it's probably a good idea to think about this when designing the template. If I were to make all the other parts of the watch, such as the pinions and the wheels, to nominal size, simply put, the watch wouldn't work. So now I have a decision to make. My three options are: 1, I could remake the main plate using my new milling machine with the drilling attachment I made in the previous video. Number 2, I could remake the master using my larger milling machine fitted with a DRO instead of using the 3D printer. Or finally, I can just compensate for the errors when I make the wheels and pinions by making them with a slightly smaller PCD. Before I make a decision, I'm going to play around with some options and see what works best. If you would like to support our channel and see regular progress updates, videos and articles on the watch project and others, please do check out our Patreon page. I would like to say thanks to Jack for his help with this video, as well as the BRU for the SCM, and of course our patrons who make videos like this possible. I'll see you in the next video.